Hey everyone, welcome to BCP Med. In this video, we're going to be diving deep into the dipole moment associated with chemical bonds. We're going to be taking a look at what exactly makes an electric dipole, how electronegativity impacts the dipole moment, how a dipole moment can be calculated, and what some chemical factors are that influence its magnitude. Let's go ahead and get started. First and foremost, I want to go ahead and define what exactly an electric dipole is to begin with. A dipole is a system containing two opposite charges, one positive and one negative, each of magnitude q, which are then separated by some distance d. Dipoles, or the dipole moment more formally, are considered vectors, and in chemistry are said to point in the direction of the negative charge in the system. So in this case, the dipole moment would be denoted by an arrow pointing to the right, towards the negative charge. The crosshatch on the left side of the arrow is to indicate that that is the positive end of the dipole. The convention is a bit different in physics, so it's worth noting this is the format for how chemical dipoles are denoted. In fact, in physics, the arrow points the opposite direction. Mathematically, the dipole moment is often represented by the Greek letter mu, which we will see in some equations later on. Now, a defining trait of electric dipoles is that they respond to the presence of an external electric field. The electric field lines, denoted by these purple arrows here, are going to rotate the dipole embedded within them, such that the chemical dipole arrow, the black arrow indicated above, will rotate to be anti-parallel, pointing the exact opposite direction of the electric field lines. We can go ahead and look at this here on the right-hand side of the screen, where the positive charge is essentially being pushed forward downfield by the electric field lines, while the negative charge is being pulled upfield. This is particularly useful information in an empirical setting because an electric field can be used to determine whether a molecule contains a dipole experimentally, since it will rotate polar molecules into alignment with the field while not impacting nonpolar molecules whatsoever. So, if the dipole moment is a vector, as we have specified, it must have some magnitude, and this magnitude is going to be different for different cases. The dipole moment is denoted by the Greek letter mu, and is going to be equal to the magnitude of the assembled charges times the distance between them. In chemistry, the dipole moment is often measured in units of Debyes, after the scientist Peter Debyes, and it has a magnitude of 3.3 times 10 to the negative 30 coulomb meters. Let's go ahead and look at an example calculation. The hydrogen atom involves an electron orbiting a proton at some average radial distance. While the position of the electron is probabilistic, at a given observation it is fixed in space, such as in this Bohr model shown below. The hydrogen atom here looks quite a bit like the electric dipole example from earlier. In fact, it's almost identical, with the proton being our positive charge on the left, and the electron being the negative charge on the right, separated by some distance d, which in this case is the orbital radius. Now, we want to go ahead and treat this hydrogen atom as such, as an electric dipole, and determine what the magnitude of the dipole moment is for the hydrogen atom fixed in this particular moment in time. To do this, we're going to go ahead and take our Q value for the dipole as the elementary charge of a proton and an electron, and we're going to use the D value as the average orbital radius of the electron at 0.5 angstroms. We are then going to go ahead and apply our mu equals Q times D relation to solve for the dipole moment. To use this formula, though, the charge needs to be in terms of coulombs and the distance in terms of meters. So we're going to go ahead and convert our elementary charge from 1e, one elementary charge unit, to 1.6 times 10 to the negative 13 times 10 to the negative 19 coulombs, and the distance from 0.5 angstroms to 5 times 10 to the negative 11 angstroms. We're then going to go ahead and plug in these values into the equation and multiply them together. And this is going to give us a dipole moment of 8 times 10 to the negative 30 coulomb meters. However, this is not a very useful unit in chemical sense, so we're going to go ahead and convert that back into Debyes using the unit conversion at the top of the page, which is going to give us about 2.4 Debyes for this hydrogen dipole. This would be the magnitude of the hydrogen atom at a fixed moment in time. However, in reality, because the electron is moving all around the hydrogen atom in this wave-like fashion, the average dipole is going to be 0 since the wave function is spherically symmetric. Now, because the dipole moment can be measured experimentally with electric fields, we can use it as a tool to calculate the partial charges on a polar molecule. That is because mu can be measured and d can also be measured, so q, our value in the equation here, can be easily calculated. For example, let's look at the HCl molecule. We could see that this molecule is polar without any calculation, since Cl is going to be much more electronegative than H, and so the dipole moment arrow is going to point towards the right, towards the Cl, which is going to carry a partial negative charge. However, from this theory, we have no idea what the actual partial charges are on the Cl molecule, or the the Cl atom or the H atom. Experimentally, the observed dipole moment, though, is going to be 1.1 Debye, and the bond length, which represents how far apart the partial charges are, is going to be about 1.3 angstroms. So to calculate the partial charges, what we're going to want to do first is get these values into our standard units. We're going to convert our 1.1 Debye into Coulomb meters, which we have here, and then our angstroms into meters, which is going to be 1.3 times 10 to the negative 10 meters. Now, currently, our equation is in the form to solve for dipole moment, but we want to solve for the partial charges on each atom for Q. So we're just going to do some algebraic rearrangement here to get that mu over d is going to be equal to Q. Now, at this point, we can simply plug in our values for the dipole moment in terms of Coulomb meters and the value for the bond length d in terms of meters and solve for Q, which is going to turn out to be 2.8 times 10 to the negative 20 coulombs. Now, that's all well and good, and that is in fact how much charge is on each atom. That said, this is not very intuitive in a chemical sense. So we want to go ahead and convert it back into electron units of charge. And we do that simply by dividing by the Coulomb to electron charge ratio, which gives us that we have a Q value, a partial charge of 0.176 electrons. Now, this is significant because if we go ahead and make this a percentage, what this tells us is that the H and the Cl each have about 17% of an electron charge as their positive and negative charges respectively. If this charge were to be 100%, right, that would mean that there's one full electron transferred from the H to the Cl. That would be an ionic bond, right? If that were a sodium, we would see a near 100% electron transfer, near 100% charges. So in a way, this percentage value tells us how ionic the compound is. If 0% is a perfectly balanced covalent compound, like a diatomic hydrogen, let's say, where there's no electronegativity difference, and 100% is an ionic compound, the percentage scale between there tells us, well, where do we fall between those two ranges? It's a measure of molecular polarity, and it's actually a metric called the percent ionic character. And it's very useful in determining things like acidity and boiling point and how well a compound is going to dissolve in a polar solvent. Now, because the dipole moment is related to charge separation, it is intimately related to electronegativity as well. Q is determined by the amount of charge separated, that is what Q literally is, and a larger electronegativity difference is going to mean a larger charge separation, more charge being pulled by the electronegative atom from the less electronegative atom. So the dipole moment arrow is then always going to point from the less electronegative atom, which here we're defining as H, towards the more electronegative atom, which we're defining as Y. And that's why Y is going to carry a partial negative charge and X a partial positive charge. And we can look at some real data to corroborate this relationship between electronegativity and dipole moment. So, for example, if we look at some carbon nonmetal bonds, and we're going to look at the electronegativity as it increases from the nonmetal and how the dipole moment changes. On the left, we have three bonds, carbon-nitrogen, carbon-oxygen, and carbon-fluorine, where the electronegativity of the nonmetal is increasing downwards down this column, right? F being the most electronegative. If we look at the dipole moments, we clearly see that the magnitude of the dipole moment, the polarity of the carbon nonmetal bond, increases very nicely as the electronegativity of the nonmetal increases. Clearly, the more electronegative the nonmetal is, the more polar that bond is, the larger the dipole moment associated with it. We're also going to see a very similar pattern with the hydrogen halides. If we go ahead and arrange these from left to right, as the electronegativity increases from right to left here, with fluorine being the most electronegative and iodine the least, we would expect the dipole moment to increase from right to left as well. HF would be the most polar compound, having the largest dipole moment in terms of Debye, and HI would be the least polar, having the weakest dipole moment. And indeed, if you went ahead and looked at the empirical data, you would find that that is true. Another thing we want to pay attention to is that the dipole moment is also a function of distance, which in this case is the bond length of the molecules at play, right? Mu is not just a function of Q, right? It's not just related to electronegativity and charge separation, but also how far apart those charges actually are. To begin, let's look at fluoromethane, a fluorocarbon species, right? It is denoted by the structure below, and it's going to have one CF bond. Fluorine has an electronegativity of 4, which is extremely high, so we already know this is going to be a polar CF bond. And it also has a bond length of 140 picometers associated with it. This particular combination is going to result in a dipole moment of about 1.85 Debye for the CF bond, or for the fluoromethane molecule overall. Now, let's look at a very similar species, chloromethane, which has a Cl substituted for the F. Chlorine is a bit bigger than fluorine, which is represented in the diagram as a larger green sphere. Now, chlorine is going to have an electronegativity of about 3, which is markedly less than fluorine. So, based on that, we would expect, well, lower electronegativity, it's going to pull less strongly in the electron density and have a lower Q value, a lower charge separation. However, we also see that it has a larger bond length at 180 picometers. If we based our prediction solely off electronegativity, we would expect a lower dipole moment for this bond. However, rather interestingly, it turns out that this molecule is actually more polar than fluoromethane, having a dipole moment of 1.87 Debye. This is because the larger bond length, d, means a greater separation of those partial charges, even if they are smaller. Indeed, if you were to calculate the partial charges, you would find that they are much smaller for the CCl bond than for the CF bond. But nevertheless, the chlorine species is going to be more polar due to the larger charge separation. So it is important to remember we have these two factors at play, not just electronegativity. A different factor, which also has a profound impact on bond dipoles, is the order of the chemical bond. In general, the higher order bond, a double or a triple bond, is going to have a higher dipole moment than a single bond. Now, there are two reasons for this. The first is that there's simply more electron density to be withdrawn when the two atoms are participating in higher order bonds. We're no longer just dealing with 2 electrons, but 4 or 6 in the case of a triple bond. So the more electron density that can be pulled by the electronegative atom, the bigger the buildup of partial charges you can get. I think this is a pretty intuitive way of looking at it, because it's almost like you're having a tug of war between these two elements. If you give the bigger element an opportunity to pull on more stuff, it's going to take more, right? The second factor, which is arguably more important, is a little bit tricky, and that's the resonance characteristic of pi bonds. Pi bonds behave a bit differently than sigma bonds and can localize electron density more on one atom than the other. Now, the thing is, I don't want to cram the effects of resonance on dipoles into this video, as it's a very important subject, and I want to give it its due time, so I'm going to go ahead and make a separate video to address that in depth, because there's some really fascinating things that can happen. However, for now, I just want to be aware that all else equal, a higher order bond between the same atoms will be more polar than a single bond between those atoms. And we can look at some data, right? So if we look at methylamine, it's going to have a CN single bond, which is going to have a dipole moment of about 1.31 Debye associated with it, because N is more polar than N is more electronegative than C. Pretty straightforward. However, if we look at methanamine, which has a CN double bond, clearly it has a larger dipole moment at 2 Debye. Nothing else has changed in the molecule really, only that we now have a pi bond added, so there's more electron density being pulled by the nitrogen. Similarly, if we go ahead and increase it one step further to the triple bond, we see that the hydrogen cyanide molecule has a dipole moment of 2.66 Debye, meaning that the CN triple bond is by far the most polar out of these three, which, again, based on our understanding, makes perfect sense. Even now 6 electrons are being pulled by the nitrogen away from the carbon, and if you go ahead and watch our resonance video, you'll see why that makes sense from that point of view as well. The moral of the story is more bonds equal more polarity. One last thing I want to do is present how we can use the magnitude of the dipole moment to gauge the practical polarity of a molecule. Obviously, from a rigorous point of view, Any molecule which has an electronegativity difference between atoms, and that means any molecule with different atoms in the bond, is going to have some degree of dipole moment, since any difference in electronegativity is going to lead to some degree of uneven charge distribution. However, do we really care if a molecule has a dipole moment of 0.1 Debye? I mean, does an electronegativity difference of 0.1 units really matter? Well, it depends on the application. For some spectroscopic things like microwave spectroscopy, it matters a lot. But for general purposes like IMF considerations, we only care about larger differences in polarity. The typical rule of thumb that is used is that a difference of an electronegativity less than 0.5 units is going to be considered a nonpolar bond. And the classic example is the CH bond, which only has a difference of about 0.3 units and is considered completely nonpolar. A polar bond is going to have somewhere between 0.5 and 2 in terms of its electronegativity difference. So for example, if you look at the HCl molecule, it has a difference of about 1 unit. So it's going to be a nice polar covalent bond right smack in the middle of our definition. The ionic bond is going to be defined as something with an electronegativity difference of greater than 2 units between the atoms. And you really only see this between metals and nonmetals. It's very odd to see it between two different nonmetals, although certain cases can lead to such situations. And the canonical example that we'll see often is the sodium chloride bond, where you see about a 2.2 unit difference between Na and Cl, and that's going to be very nicely ionic. So with that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you enjoyed what you saw, please like and subscribe to the channel. Make sure to check out our other videos in the chemistry playlist to learn more, and if you're looking to branch out a little bit, check out our other science playlists as well. See you next time!